So yeah, indeed, I'm finishing my PhD about shape optimization for additive manufacturing. But the work I'm presenting here is something that I had started before during an internship with Natasha Vermaak in Lehigh University about how to optimize the shape to, well, design an object that would have a shakedown, well, that would have a shakedown behavior. So, no, sorry, just some context. I don't know if you're all familiar with shape optimization, but basically the objective is to design an object so that it answers as well as possible to some constraints. So for example, here we have an initialization. We're pulling on this side, we fix this side, and we want to minimize the compliance with a fixed volume. And so for example, we have some tools that allow for building an optimization algorithm that will redistribute the material to fit as well as possible the constraints that we have set in an optimization problem. And so, well, the thing we started to think about this because, because actually designing the object can have an influence on the elastic behavior it is gonna have. So we know that we have different kinds of behaviors. Well, basically in this work, we have decided that we apply a cyclic loading between 0 and the maximum value. And we want the object to be able to not to have some low cycle fatigue. So we want to be able to cycle several times without inducing any cracks or damage. So in this figure, we see that we have two different behaviors that allow this. This first, elasticity. So in this one, we don't allow any plastification. And so in the braid diagram, we see that it is this part. And then we have another one, which is shakedown, into which we allow some plastification on the first cycles. And this first plastification then brings the object back into an elastic behavior. And so we then can cycle many times without resulting into cracks. And we see that the shakedown part is here. So we see that actually the elastic, the non-plasticity behavior is a special case of shakedown. And what already exists a lot in literature, for now, is how to do some shape optimization under non-plastification constraints. So I will also call them under von Mises constraints in the following. And what we want to do is to optimize under a shakedown constraint, because so that it's not as strict as non-plastification, and it still allows for high cycle fatigue behavior. And we think that it would be able to design with, for example, removing more material under a shakedown constraint than non-plasticity. So just to introduce further, the main tools, I will just talk about what is already done, which is shape optimization under non-plasticity constraints. And to do this is just to make sure we have all the same notations. So we are considering an ideally linear elasticity equation. So we apply a cyclic loading between 0 and J here. And so we have a Dirichlet boundary condition on which the displacement is prescribed, and then the rest of the boundary of omega is fixed. Is free. I'm sorry. And then that gives an elastic displacement that I will call ideal elastic displacement. And we want to optimize under a von Mises constraint, so we don't want any plasticity. How to characterize this? Well, basically the actual stress within the solid will be the ideal elastic stress whenever this stress satisfies this von Mises condition. And it will be a stress satisfying this equality when this ideal elastic stress is getting too strong. So intuitively, if we're in a good basis for the stresses, it means that the ideal elastic stress, when it remains in the circle, then we don't have classification. But as soon as we get out of the circle, then, this ideal elastic stress is out of the circle, and the actual stress has to follow the boundary of the circle here. And this means that we have classification, which we want to avoid. And then with this formulation, we get an optimization problem. So in this work, what we want to optimize is the weight. We want to not to use much material and to get something as light as possible. The compliance is only here for a stability reason, so I will not talk much about this compliance here. And we have also the constraint that we don't want any plastification. So at each point of the shape that we have designed, we want to make sure that the ideal elastic stress satisfies this inequality. And we still have U, which is the elastic displacement. So basically, well, that's the optimization problem. And then with such an optimization problem, we have three different issues. The first one is the fact that this constraint is pointwise. So it means that for each, well, numerically for each nodal point in the mesh, we will have to satisfy this. So that makes several constraints and it cannot be dealt with directly like this in an optimization code. The second problem is that we have here a partial differential equation constraint. I will not talk much about that, but that's introducing an adjoint function in the computation of the derivative for this optimization problem. We can deal with this problem easily. And finally, the optimization variable is a shape, but that's the whole purpose of shape optimization. So I will tell this. So first, the pointwise constraints. Well, there are several ways to deal with this, this issue, because that's something that has been widely studied. What we use here is something very basic because we wanted to focus on Shakedown that I will present later. And it's basically saying that we want at each point this function to be smaller than 1. And then we apply a function phi p so that we will penalize whenever this is above 1. And then we integrate. So we sum all the pointwise constraints to make only one constraint that will, into which the integrand is actually, will actually say whenever this is above 1. And so with this only one constraint, we can, well, very easily include it into an optimization algorithm with an augmented Lagrangian method. So that's very classic for optimization. So the second problem that I wanted to explain is how to deal with the fact that the optimization variable is a shape. So we have different ways of doing it. First, intuitive idea would be to discretize the boundary of the shape and then express the whole optimization problem depending with respect to these discretization points, and then differentiate with respect to this discretization. But that's not what we're doing here. We actually try to keep everything in the continuous, in a continuous formulation as long as possible. So we have the boundary of the shape, and we want to know how the optimization problem is going to vary when we vary this boundary with respect to a field theta. So we will move the boundary with respect to this field and then get how each of the objective function and constraints are going to vary. And thanks to this theory, we actually know that, for example, such a function will have this kind of derivative, and then we can differentiate the whole optimization problem, and we can apply a very simple gradient descent here, because if we had only one objective function like this, we would have this formulation, and we only have to correctly choose the vector field theta to make sure that we are decreasing the objective function. So that's what we do, and we get an optimization algorithm in which we initialize the shape, compute the objective function and the constraints, and then we compute this derivative and, well, transform it into an advection velocity to move the shape. Then we proceed to shape variation. So we are here representing the shape is a level set. And so we move this level set thanks to a Hamilton-Jacobi equation. We compute again all the different quantities that are involved in the optimization problem. And then in case of an improvement of this optimization problem, we accept the iteration and, whoops, sorry, update everything. And if it's not, well, if we have not improved the optimization problem, we go back to this step, and we here have a coefficient that determines how far we are pushing the boundary on the direction of the gradient. And we just simply decrease this coefficient to make sure that we're improving the optimization problem.
Mathilde,
so that's something. Yes.
You are still without plasticity effect.
Here actually I want to optimize without plasticity. Yeah.
Without yet. Okay. Mm-hmm.
Yeah, that's the purpose of this constraint. So no plastification. And so that's the first result. So we have a case here in which we pull in the middle. We fix here, we have a Dirichlet boundary condition. We initialize with this shape. And then here I present two results. So the first one is if we were not applying, if we don't care about plastification, we don't add any constraint. We only optimize the volume with a small compliance. Then we get to this result with very thin bars. The volume is very good. But on the other hand, since we have not put the plasticity constraint, we see that we have plastification here and here. And then adding the constraint, we see that the bars have thickened, especially in the middle, but that helped for getting rid of plastification. And so, well, the plastification constraint is smaller in this case, but on the other hand, the volume is higher. So that's just to illustrate and to present a bit of shape optimization. But actually, and then we have the result for the L bracket. So we pull here, we fix here. And in the L bracket, the problem is always in the corner here. And so we see that when we add the van Mises constraints, actually the code removes the material in the corner to smooth the shape, and so that we don't have plastification anymore. But what we wanted to do is to optimize under a shakedown constraint. So that's something that has not been widely done as it has been, as the non-plastification constraint. It was widely studied. And just to get some intuition about what shakedown is, basically before we wanted the ideal elastic stress to remain within the circle. So now we will allow some plastification. So we allow the ideal elastic stress to get out of the circle. But we want to make sure that when we will, so for example, here we load, the actual stress is here. And when we unload, we see that we remain within the circle. So starting from this point at the next cycle, we see that loading and unloading will always make the stresses remain in the elastic domain. So this means that on the first cycle, we had plastification, but then this plastification induced a residual stress rho that brings back all the system in an elastic, behavior. And so here we see that if we increase the loading, so we get something, a higher ideal elastic stress, and we see that we're getting out of the circle here. So we don't have shakedown because we will keep on plastifying each time we apply the loading. So how to optimize under this condition? Because you see that here, what I have just explained is that we need to compute this residual stress to know if we have shakedown or not. And actually computing the whole loading history is expensive. And in optimization, we need to simulate several times the process. So it would mean getting several times the loading history, and that's, computationally too expensive to be done like this. But actually, we can characterize shakedown through direct methods, and especially Melan lower bound theorem that says that a structure will shake down if it exists a stress rho such that this stress remains in the circle, so it satisfies the van Mises condition, and this stress plus the ideal elastic stress remains in the circle. So that's exactly this case here. The stress is in the circle, and the stress plus the ideal elastic stress remains in the circle. And this stress has also to be self-equilibrated. Indeed, when we unload, we don't have any loading applied on the object, and it has to be a stress, so it has to satisfy an equilibrium equation. So now how to include this in an optimization problem? Because adding an existence constraint is not easy. And the idea is that we are now optimizing both the shape and a stress, assuming that if the constraints are satisfied at convergence, this stress will satisfy these constraints, and the shape, with respect, this stress associated to a shape will satisfy this constraint, and it will mean that the shape found will shake down. So that's the optimization problem that we describe here.
Sorry, Mathilde.
Yes?
And you want to get rid from Shakedown or
I want to be in under Shakedown. I want to
under?
find a shape into which this is satisfied.
Okay, so at this point, you still want to avoid plastic deformation.
I allow plastic deformation on the first cycle, but I want to make sure that after these first cycles, we go back to an elastic behavior.
I see.
That's a bit less strict because we can have some residual stresses occurring in the solid, but we want to make sure that these residual stresses will not, after several cycles, create damage. We want to make sure that after several cycles, we will go back to an elastic behavior. So yeah, that makes a new optimization problem into which we now have the shape and a stress. And the stress must satisfy, the pointwise constraint, we can deal with it the same way as before. So we now have a constraint that says that the residual stress must remain in the circle at each point, and that the residual stress plus the ideal elastic stress must remain in the circle at each point. Well, we are still minimizing the volume. And this stress must be self-equilibrated, so it means that it has to satisfy this equation. Well, we could say that it's easy and we can apply the same things as before, but the problem we have now is that this is not really, that is a partial differential equation, but it does not have a unique solution because there is no condition here on the Dirichlet boundary condition. So we cannot use the same method as we have used for this equation to this equation, and we have to find another idea. And so we're not using a gradient descent anymore. We will use a projective gradient descent because it happens that the self-equilibrated space is in direct sum with a complementary space that is easy. And well, the direct sum of both makes actually the total stress space. So if we choose if we optimize a stress space in this domain and we project it onto this space, we will have a correct result. And the projection on K is actually easy because it only involves a partial differential equation here. And we know how to deal in an optimization code with a partial differential equation to which there is only one solution. And so we finally get to an effective optimization problem, optimizing the shape and a stress in the whole domain of stresses with always the same constraints. But we see here that we don't have rho anymore. We have the projection of rho onto the space of self-equilibrated stresses. So here and here we have the projection. And so now we characterize the displacement U with the same linear elasticity equation. And then this eta that is involved in the projection is computed through this partial differential equation. And then we can optimize the same way. And we can notice something here is that if we fix the tilde rho to 0 and we don't optimize it, we actually go back to the optimization problem I was presenting in the first part with no plastification allowed. And now I go to the results. So that's the same test case as the first one I've presented before. So we run it only on half of the domain. We pull here and we fix here. And on the first line, we don't consider any constraints. So we don't care if there is plastification. We only minimize the volume plus compliance. And of course, the volume is the smallest because we don't constrain the problem. But we have plastification here, here, and here. And applying the Van Mises constraint as we did in the first part, we see that the bars are thickened. So as we have already seen, the volume is increased, but the Van Mises constraint is decreased. And we see here that, indeed, we don't have any more, we have no more red here and a lot less here. And then we apply with the shakedown constraints and we see that, the bar is thickened a little. We have some modifications here too, but the volume is increased, but not as much as it was under the non-plasticity constraint. We see that a residual stress is created within the solid, but this residual stress remains within the circle at each point because you see that we don't have any red on the figure. And well, indeed, the constraint related to this remains very, very low. And then the effective stress, so residual stress plus ideal elastic stress, is a lot better than it was here. And it's even better than it is here because we don't have any more red here. We don't have any red here. We just have some here. And we see that the constraint here is actually smaller than it is under a non-plasticity constraint. So, well, it demonstrates the fact that with a shakedown constraint, we can get a volume that is lower than when we don't allow plasticity with still a correct behavior. And that's the same with the L bracket. So in ideal plasticity, we get the smallest volume. With non-plasticity constraint, that's the highest volume. And it gets rid of the part here, of the material here to smooth. And in the shakedown constraint, we see that it creates a residual stress, which is non-zero, but so that it can get an intermediary volume with, well-satisfied elasticity constraints. And so the objective is now to, will be further to keep on working on this, and especially shakedown is not the only behavior to satisfy some, well, this kind of theorems and direct methods. And we were wondering if maybe we could apply this to hardening or some other behaviors to still optimize the shape under different kinds of behaviors. And for further information, we are actually in a submission process for an article describing this. And we also had published something to visualize better shakedown and to better understand the process in a mathematical point of view, well, earlier.